Yes, class, am I audible to all of you? Fia, Chavez, Austin. Is it audible?
Yes.
Alia, Humam. Okay. So yes, in the last class, we have completed all the individual circuits. Yes. All the individual circuits we have completed, circuit having only inductor, circuits having only resistor, circuit having only inductors, right? Resistor, capacitor, and inductors we have completed. Now I told you we have to start with LCR circuit, but before that, let us at least complete some one or two questions based upon this. Questions we didn't do in the last class. This capacitor one. I wanted to discuss this C class. This is written in a haphazard manner, but you'll be able to write the summary like this. First, write it down, then I'll discuss the question. See, let's just revise what we have done. And if you try to write this in one single area of your notebook. Don't elaborate it. Try to concise it and write in one just portion, because when you will be revising, see, right now you will have to go through every note. But once you are done with everything, right? Once you are done with all the portions, then this will act as a final revision for you. So see, when we talk about circuits having only resistor, E is equal to E naught sine omega t, I is equal to I naught sine omega t, right? And then current and voltage both are in the same phase. I naught is equal to E naught by R, I RMS will be E RMS by R. They are in the same phase. When we come to inductor, their current lags by 90 degree, or you can say voltage leads by 90 degree. So in such cases, E is equal to E naught sine omega t, but since current is lagging behind, you can write sine omega t minus pi by 2. Or you can write E naught sine omega t plus pi by 2. Either you can write this as minus pi by 2, or you can write this as plus pi by 2. Both have the same meaning, that EMF is leading by 90 degree and our current is lagging by 90 degree. So here we have a special value of resistance, that is XL. I naught is equal to E naught by XL, E naught by omega L. So IRMS is equal to ERMS by XL. Fine. Then we come to this capacitor, circuits having only capacitor. E is equal to E naught sine omega t, I is equal to I naught sine omega t plus pi by 2. So here you can write sine omega t minus pi by 2, or here. Wherever you are writing, don't write both the things simultaneously. And when you are writing this, then see, when you are subtracting, then only you are getting pi by 2 left. No, if you will write pi by 2 here also all together, that will nullify it. It will become 0. All right. So either you can write, I prefer to write like this, because remember one thing, other will be remembered automatically. Like if I try to remember current lags by 90 degree. So minus pi by 2. Here it's leading, so plus pi by 2. Remember one thing, so that it is helpful. Now here we talk about capacitive reactance, which is 1 by omega c. All right. So do one thing, just note down this part. See, when we say I is equal to I naught by root 2. So here, I naught's value for every circuit you can write, like E naught by 1 by omega c, E naught by omega L, like this you can write every time. All right. Depending upon whatever is asked to you. So I naught by root 2 and E naught root 2 by 1 by omega c. Like this you can write it. Note down this as a summary. Just make the heading as summary. Write it down. Then I'll discuss the questions which are left. All right. First note this down. That's omega C. Omega is angular frequency, C is capacitance. Yesterday we did no same omega C. C class. The question says that a pure inductor of 25 millihenry is connected to a source of 220 volt. Find the inductive reactance and RMS current if the circuit if the frequency of the source is 50 hertz. See, inductance is given to you as 25 millihenry. So we'll convert this into 25 into 10 to the power minus 3 Henry. Okay. Then ERMS value. What is the value of source? 220 volt. So ERMS value is 220. Whatever is given no within the circuit which is rotating, that is 220 volts. Okay. Find the inductive reactance and RMS. Frequency is given as 50 Hertz. We have to find out inductive reactance XL and IRMS. See, if we find out XL, we'll be able to find out IRMS because that will be just with the help of ERMS and XL. What is XL? It's omega L. Do we know omega? We don't know omega. But we know nu, that is frequency. So you can write this as 2 pi nu into L. So this becomes 2 into 3.14 into 50. L is 25 into 10 to the power minus 3. This is the whatever value of XL comes that you can cross check later. And then value of IRMS will be ERMS 220 divided by this term 2 into 3.14 into 50 into 25 into 10 to the power minus 3. Please let me know what is the value of IRMS coming. Write it down. Let me know. Text me in the chat column. What's the value of IRMS coming? Don't calculate it separately. Calculate it here directly. How much earlier IRMS is coming? 28 amperes. Okay, so this is 7.85 ohms. Okay, thank you, Alia. 7.85, no? 7.85. This is ohms and this is 28 amperes. Correct. A coil has an inductance of 1 Henry. What will be the frequency? What will be the frequency? Will it have a reactance of 3000? At what will be the frequency? It will have a reactance of 3142 ohms. Okay. See, inductance is given. So Excel nobody has calculated till now. Reactance only you have to tell. L is already given. XL is given as 3142. You have to find out nu. This you didn't find. The calculations are also very easy. See, 3142. It will be cancelled by 3.14 value of pi. See, XL is equal to 2 pi nu L. So from here, frequency will be equal to XL. Alia, just check your calculations. I think a silly mistake you have made. Just check Alia once again. So this becomes 3142 divided by 2 into 3.14, right? You can ignore this 2 also for the calculation. Answer will come same. Kya bacha? L is 1 itself. See, this, take this as 314 only. 3.14 is coming. So approximately 2 zeros are over there. That becomes 100. 100 by 250 it should be. Please, someone else also confirm, because Alia, your is 500 coming. No, just check. It should be 500 or 50 hertz. Next part, someone please cross check this. Next part says that what should be the capacity of a capacitor which has the same reactance. So now capacitive reactance's value is 3142 this time, and you have to find out the value of C, capacitance. So second part, XC is given as 3142 ohms. So XC will be 1 by omega C. This is 1 by 2 pi nu C, 1 over omega C, right? So C will be equal to 1 over 2 pi nu XC. So this is 1 over 2 into 3.14 into frequency, I think 50 or 500, please check. And value of XC, not XL, this will be 3142, this much of farad. Please write it down and keep on letting me the values also. I'll just write it on the screen. It's 500 only. Okay. So just write down here also 500. Because 2 students are getting it. And if this is 500, someone please calculate this also. First write it down. Okay, you are also getting 500.31 exactly. Okay, this value is 500.31 hertz. Nearly zero, it won't come. 1.013 farad. Okay, then. Something 1 point, it should be around 1 point. Fine. Let's start with LCR. See, when we talk about LCR circuits, in the same circuit, you will be having resistor also, you will be having inductor also, you are having capacitor also. This is resistor, this is inductor, this is capacitor. Okay, resistor, inductor, and capacitor. See, when we were talking about resistor, so current and voltage, let's say voltage of the resistor is VR. So voltage of the resistor, both were in the same phase, right? This is how it will be depicted. So VR is equal to I into R using your Ohm's law. When we talk about inductor, this is current, this is inductor, this is current, and we know voltage EMF is leading by pi by 2. So here the value of voltage of this inductor, this is current into XL. IR, similarly, when we talk about the capacitor, see, current is leading the voltage by pi by 2. So VC will be equal to I into X. All right. So you have to use your Ohm's law. Now I'll draw the same thing in the phasor diagram. When we talk about the phasor diagram, see, one is standardized, one is fixed, that is your resistor. This is, let's say, VR. Now, value of VC and VL, that is voltage of the inductor and voltage of the capacitor, both can be different. It can happen that one is greater value. Resistance is fixed. We have taken because it is in the same phase. Let me show you this first. Suppose this I have taken VL. This I have taken VL. And here I have taken VC. Fine. Now see, if suppose, let's say you can have two cases in here. When we are talking about this, you can have two cases over here. If VL is greater than VC, suppose voltage of inductor is greater than voltage of capacitance. So see, it's like one vector is here, one vector is here. If this vector is greater, so when you will subtract, when you will write VL minus VC, resultant will be in this direction because this is greater. That's how we subtract two vectors. In the direction where the vector is greater, there you put the sign, right? It is greater towards VL. VL is greater this time. All right. So because of this, XL is also greater than XC. It means this is the case. Your VL minus VC will be here while your VR is here. Clear? Okay. Here you will be talking about XL minus XC because VL is greater. But let's reverse this. If you are reversing it, if you're saying VC is greater than VL, it means resultant is downwards. This is like, this is VR and here this is VC minus VL. You will write VC minus VL. That is XC minus XL. Whenever we are talking about LCR circuits, resistors case is fixed because it is in the same phase. But when we talk about VL and VC, they are phasors. They are not simple values that you can simply add or subtract. They are vectors. They are phasors. They cannot be added directly. Now their resultant will be taken. The way we have, if we have three vectors and we have to apply parallelogram law, are we able to apply parallelogram law on three vectors? No. We take two vectors, we solve them, and then the third one is used. Similarly, this is what we are going to do. So suppose if VL is greater, then VL minus VC will be taken in this direction. If VC is greater, so VC minus VL will be taken in this direction. That's what I'm saying. All right. One more thing, you have the concept of impedance. Acha, do one thing, note it down, then we'll talk about impedance triangle here in the next section. Note down this. Any doubts you have, let me know. Done, class? See, now coming to impedance triangle. See, impedance triangle is nothing. It's impedance is also resistance. Now, when we talked about circuits having only resistor, so only resistor was present to produce opposition in the flow of current, right? Then when we talked about circuits having only inductors, then there you were having only XL that was present to perform the opposition work. Then we talked about circuits having only capacitors. So XC, capacitive reactance, was present to oppose the motion of current, flow of current. Now we are talking about a circuit which is having LCR, inductor, capacitance, and um, inductor, capacitance, and resistor. All the three are together present. Now, individually, it will be having resistor, inductive reactance, capacitive reactance, right? Resistance, inductive reactance, and capacitive reactance individually will be present. But there will be a net resistance of the circuit, net current in your circuit, net EMF in your circuit, right? So that net value of resistance, overall resistance, that is a term instead of using the term resistance, because otherwise it will be similar to the term actual resistance, right? So we use the term impedance. So impedance basically means what? Impedance means the resistance of the entire LCR circuit. Resistance of the entire LCR circuit. This is what is meant by impedance. Fine. So when we talk about impedance triangle, two cases can occur. Triangle, we just write it for our calculation purpose so that it becomes easier for us to understand and derive it. XL can be greater than XC, and again XC can be greater than XL. So two cases we'll discuss. So suppose this is XL minus XC and this is resistance. Means this is actually depicting what? This is depicting main value of E naught of the circuit, the resultant. This is depicting VR, potential of resistance. This is depicting potential of inductance minus potential of capacitance. Right? Now, if you apply Pythagoras theorem over here, so this becomes E naught square will be equal to VR square plus VL minus VC whole square, right? H square is equal to P square plus B square. On applying, what we can do, E naught square, keep it like this. VR is what? I naught into R, its whole square, plus what is VL? I naught into XL minus I naught into XC whole square. This is how you can write it. One thing we can take, I naught square, at least we can take common from all of it, I naught square. So what is left from here? R square is left. From here, XL minus XC square is left, right? So what is the value of I naught? What is the value of I naught? I naught square is equal to E naught square divided by R square plus V naught. XL minus XC whole square. Yes, this is the value. So what is I naught equal to? I naught is equal to E naught divided by under root. Here square got cancelled, but there wasn't any square. R square plus XL minus XC whole square. Now compare. I is equal to V by R. Net current of the circuit is equal to net voltage divided by net resistance. What is the impedance equal to? Under root R square plus XL minus XC whole square. This is the value. If it is just your resistor circuit, Z is equal to R. If it's just the inductor circuit, we used XL. When it was just capacitor circuit, we just used XC. But when all the three are present, and if VL is greater than VC, you use this. If XL is greater, this condition is only valid if XL is greater than XC. Suppose reverse. XC is 5 ohm, XL is 3 ohm. Let's reverse the condition. So this sign will just change. See, Answer will come XC minus XL whole square. That's it. Same thing, it's just that XC minus XL whole square will come. So depending upon the question, you can keep on interchanging this. VL, you have to write it as XL minus, this is actually X naught. This is XC minus XL, or when you have to use XL minus XC depending upon the value. So what is impedance? Impedance is basically effective resistance of the series LCR circuit, which opposes or impedes the flow of current through it. Basically, in simple terms, you can remember net resistance of LCR circuit. Individually, now you know when you have combined all of them. So that is Z impedance. Now see, one more thing. Apart from impedance, this triangle is also helpful in calculation of tan phi. Suppose this is phi. Phi is just the value of phase I have chosen. Phase differences don't occur. Phase differences between the current and voltage. Let me take this as phi. So what your tan phi will be equal to? See, if your XL is greater than XC, see from this triangle you can find out many things. Impedance triangle. Tan theta will become perpendicular upon base XL minus XC by R. And if it is XC greater, so tan phi will become XC minus XL by R. This you can keep on interchange. One more thing, cos phi. Cos phi is equal to what? R, that is the base, by the hypotenuse is Z. Here also, cos phi is R by Z. So cos phi is the only quantity that is same irrespective of whether XL is greater or XC is greater, because in your calculation, there isn't any involvement of XC or XL. Fine? There isn't any involvement of XC or XL. Clear? Now, suppose just take an example. Let's say value of XL is given as 30 ohms. XL is given as 30 ohms. XC is given as 14 ohms, random I have taken. So this is which case? This is case XL is greater than XC. So when you have to calculate tan phi, cos phi, anything, you have to use the case XL minus XC and put down everything in the equation. All right. Now see, XL is equal to XC. This is a special case. You have a proper separate topic, resonance, we will study, where XL is equal to XC. So in that case, only VL is going to be equal to VC, where phi will be 0. This we'll be studying in detail. Otherwise, now for your LCR circuit, I naught will be equal to E naught by Z. Only resistor circuit, I naught is equal to E naught by R. Purely inductive circuit, I naught is equal to E naught by XL. Purely capacitive circuit, I naught is equal to E naught by Z. LCR circuit, I naught is equal to E naught by Z. Fine. XL, XC, R, Z. Z is combination of all the three. Similarly, IRMS will be ERMS by Z. And one relation I hope you all remember, IRMS is equal to I naught by root 2. ERMS is equal to E naught by root 2. This can also be helpful. Note down all this. Pythagoras theorem, because see, it's a right angle triangle. That's a Pythagoras theorem is the best solution. We have constructed impedance, the concept of impedance triangle, no, that has actually come so that it creates a right angle triangle and you are able to perform all these calculations. If we do this directly no, on the phasor diagram, it will be very confusing for you to relate it. What is this? Triangle law also we can use, or the impedance triangle. This is the simplest form that is used, and in your NCRT also this is given. All those who have completed, you people can start leaving. So questions of this LCR part we'll do in the next class. Please revise the basics and come. Okay. So now power, energy and transformer, this is left from us. Thank you so much, class.